I ask 20 people here, I'll get 20 different answers. But, like it will probably be something along the lines, well, we want to teach learners some skills to be successful in life. And, like I'm sure like you would give like a variant of this, but I hope nobody would like fight me too much for this definition. And then, like with that purpose in mind, like we go ahead and we build schools, we build MOOCs, we take kids out of the playground and we put them into these rooms and like, you have to learn this stuff, right? How do we know that they're learning, right? Good question. But we have an answer. We test them. And we really test them. Like, the average American student actually takes over 100 standardized tests from kindergarten to high school. And this is just a standardized test. This is not including quizzes or like the exams the teachers might give like at the end of the year. This is only a standardized test. So we give students in our society a lot of tests. Do they like this? Well, it turns out teachers don't like this, students don't like it, parents don't like all these tests. Everybody's very grumpy about this. So the question is, can we do better? And yeah, we can do better. So a cool idea to get rid of tests or to minimize them is embedded assessment. It goes by many names. Some people call it invisible assessment. Some people call it stealth assessment. And it's not. And it's an idea that has been studied previously in the literature. So the idea is like, let's make assessment. Let's make all this testing a little bit less intrusive. Let's not have to stop teaching to just give a test, and let's use the data that we can collect, that we're collecting anyways. For example, by collecting the data of learners studying, or the data that learners produce by doing educational activities, or what I'll focus in this talk, educational games. So for the rest of this talk, hopefully you're very motivated now. That was my motivation of this problem. Then I'll talk a little bit about how game data looks like. I'll do a very brief machine learning review, and then I'll talk about the main contribution of our paper. It's the SPRING method. It stands for Student Proficiency Inferrer from Game Data. Then I'll share some empirical results and then a conclusion. So, all right, let's think about how game data looks like. So this is a good example of how the data produced by students playing an educational game might look like. So it will have like, some event identifier, some ID for the users, and then like logging what activities they're doing. So, and in another hand, we might be like, we might have some training data, we actually gave them a test. And basically the idea is that, we want to map this data and predict the test, right? So basically what we want to learn is a function that takes game data and produces, and predicts what would have been the score of the student during test. So during training, we have all this data, but what we really want to do is like get rid of this. So learn this function, right? So basically, we want to map from X to Y. So let's think a little bit about how this data is. It's actually rather complicated. We can see that an observation can be multiple rows for a student. So for example, Linda has 6 rows. Tony only has 1. We have a list of events. We have slots, attributes that qualify the event. And then we have feelers. For example, Linda moved the object in these coordinates, right? And it changes for every event. So how can we do machine learning with this? So this data is quite complex. So I want to see a show of hands who is very comfortable with machine learning methodology. So about half, maybe. So if you spare me a few minutes, I'll just want to do a very quick review. So for people who are familiar with this, it will just put people in the same page. For the other ones, hopefully it will be interesting. So what I really want to make of this review is not a lecture style. It's just like to understand the complexity of the problem. So let's look let's just take a quick look of how we can model this kind of data. So one option to model data like this is like what has been done in the literature quite a bit. Valerie Schuh, Kristen DiCerbo, I think Bob Mislevy have been pioneers in this field. So basically they designed a kind of model called Bayesian Network. And this is very successful. This has been very successful for invisible assessment. So coming up with a Bayesian network can work really well, but it has some caveats. So for example, we would need experts in Bayesian networks, somebody that really knows how to put the nodes, put the edges, put the parameters, so on and so forth. And then we would need somebody that understands the games and that understands the learning theory. So it's quite an ordeal. So if you have like this team of experts, which are often not just one expert, it's actually multiple, it can work pretty well. But it requires a lot of work, and the problem is like you do all this work and it's just for one specific game. It would not generalize for other games. So another option is like, like what a lot of people in educational data mining does is like, like a feature vector machine learning approach, like you go and download WEC, or whatever your favorite machine learning package is, and you just throw the data in and see what happens. Unfortunately, the data that we can collect from these logs is not suitable for this sort of approach of just throwing the data. These sort of, like decision trees, logistic regression, they require feature vectors, and it's not necessarily obvious that how we could map like an arbitrary game log into a feature vector. The reason is because the number of events per user is unbounded, and feature vectors by definition are bounded. You need to specify the number of dimensions beforehand. And then also, like, not all events have the same slots, so on and so forth. Another option is like models that people use in machine learning for temporal data, like hidden Markov models. Again, you cannot just use like off-the-shelf technology for this, because like a model for temporal data would require that all events would have to have the same number and type of slots. So the four kind of family for machine learning models would be like kernel methods, but as far as I know, there's no kernel methods for this sort of data. So this brings us to the main contribution of our paper, which is like a method that at least the aim or like the desire we have is like we can throw some game log data and it would learn like how to model student behavior and in a way that is useful for assessment. All right. So I think I said everything from this slide. So basically our motivation is a general way to capture learner behavior, and we want to be able to confirm that learned behavior is valid by explaining test performance. So we'll learn a model that explains how students play games, and we'll validate that those models are correct by saying, well, look, this model is also able to predict exam performance, assessment performance. And we want to rely on data. We don't, we're not want to have like somebody tells us, oh, this feature of this game could be useful. We want an algorithm that learns that automatically. And for this study, we focus on an educational game that was developed in Pearson for basically research purpose. It's called Alice in Areal, and that will be our case study. So Alice in Areal, no surprise, it's about geometry. The name sort of gives it away. It's actually not just one game. Like, for all intents and purposes, the game levels are like mini games. Targets three stages of learning related to geometry: area, unit, iteration, use of unit squares to measure area, and use of composites to measure area. This is a screenshot of how it looks like. So basically, like the learner has to fill some areas, so like move these little cubes like to this part. Anyhow, maybe not so interesting for this context. So this is the outline of how our method, how our algorithm works, Spring. So it's basically a pipeline of 3 steps. On the first step, and it's very simple. We discretize slot and fillers. The second step, we model how groups of students play. And the third step, we do a regression. So let me focus on the first step first. So the discretize step, we just simply want to simplify data. So we want to convert event, slot and filler structures into a sequence of actions. So this is what we want to do. So we have like this complex data that, as we said, it's hard to model, and we want to just simplify it. So we want to remove these slot and fillers. How we do it is just by doing clustering on those parameters. So for example, so this is a screenshot of one of these mini games in Alice in Areal. So like the user, what users have to do is like move these little cubes and fill these areas. And anyhow, there's more detail like that, like advanced users would paste multiple cubes together. Anyhow, but for the context, it's basically they have to fill these spaces, right? So we can see that there's patterns of, if we do like a heat map of where users move stuff, there's some patterns. And we can use those patterns to actually do clustering. So for example, if we put like, if we use historical data where users have moved the little cubes, then we can do a clustering algorithm. So in this case, these numbers represent the output of a clustering algorithm called dbScan. We experimented with other things like k-means, whatever, right? So basically, we have what? 18 clusters plus an outlier cluster in this case. So 19 clusters. So this is another mini game, like the same idea. In this case, we will have 5 plus 1 cluster, so the outlier cluster. So basically, we translate that as slot and filler data by doing clustering into a sequence of actions. Then the second step is actually modeling how groups of students play. So we group students by their performance. During training, when we're learning this model, we have access to test data, right? So we make n groups. So for example, if we have, n equals 2, we would split high-performing students and low-performing students. You can do this. What we did is like splitting by the median. You can imagine more sophisticated approaches, like, doing k-means or whatever, right? So we split the students into these beans, and then we create a model that explains how these different group of students play the game. So the intuition here is like, imagine that like we have 10 kinds of. I cannot read this, and I apologize. So you imagine that you have 35 actions after clustering. The hypothesis here is that low-performing students and high-performing students would play throughout time differently. They would have different sequences of actions. So, this would be a visualization of how it would look like, and we're hypothesizing that for assessment, the sequence of actions of students that are really good and really bad, they are different. So what we can do is just train like an off-the-shelf model called hidden Markov models. It's a temporal model, and I'll just give the really basics of how it works. So the observables of this model are the sequence of actions the students are taking. So, like move object to this cluster, use whatever toolbox. And then we'll have some latent variables that we can interpret freely. So, we can hypothesize that those latent variables is a mental state of the student. So, for example, there might be an exploration stage, there might be a solution stage. It's up to us to interpret that, right? Then the third step is actually trying to predict the score performance. So for this, we just use like a very simple model, just a linear regression. And we just have, we just learn two parameters. We can combine the output of multiple games. So basically, what we do is, what we estimate from the game logs is like the difference of the likelihood of being in the performance group, in the high performance group, minus the low performance group. I'm being a little bit hand-wavy. So basically, we have two models. We have like one HMM, one hidden Markov model for high performing students. We have a hidden Markov model for low performing students. We can compute the difference of how likely the data that we see from the game logs, that it has came from each of those models. And then we can use that difference to try to predict the post-test performance. All right, how well does this work? So, and again, this is just a simplification. We can think of like more complex ways more complex ways than a linear regression, right? But we just wanted something straightforward. We use data from this Alice in Areal. So it basically went up with 77 students after filtering. And we use like the standard cross-validation and 80% and 80% for training and 20% split. We use data from 11 games. This is around 80,000 events that we have. So if we see at the residual analysis, I really like seeing this sort of visualization. It gives like a sense of how it behaves. So if the model worked perfectly, all the points would be in this diagonal line. So let's compare it to some baselines. We can try, and these are all regression models that we can train. So we can see if we can, and I'll be benchmarking by Spearman rank correlation, which basically says how well we can reconstruct the ranking of students in the assessment. So can we rank the students properly? Thank you. So and I pasted this cheat sheet. It basically anyhow lower numbers. 0 is like we cannot predict at all the ordering. 1, we can predict the ordering perfectly. In the paper, we have other metrics. If you hate Spearman rank correlation, this is the one that I thought it was most intuitive. So we can train a baseline just predicting, well, where students be able to solve the mini game successfully at first try. That is not very predictive. We can use the spring method that I just described, but removing the temporal order. So instead of hidden Markov model, you just have like a histogram. And that improves on the baseline, but not that much. So another thing that we wanted to try is like, well, maybe your spring is not really doing anything. Maybe it's just like students that try harder, that engage more. Maybe that's the key to predicting post-test performance. And that works okay, but it's really not that impressive. But Spring, using this idea of using the whole approach that I just explained, has on the moderate to high range of correlation. Like different metrics would give a different result. And again, like what I want to highlight here is that we are using just a very basic linear model, right? Like there's really a lot of room for improvement. We just wanted to try something really simple to demonstrate this. Anyhow, just to wrap up, the message that I want to convey is that educational games may be more enjoyable and less intrusive than conventional tests. Game data is difficult to analyze, and that this methodology, Spring, may enable us to have fewer tests for students, improve game design because we can then see like how predictive an educational game is of a post-test, and may enable automatic invisible assessment. And that's all.
We have time for questions. We're going to use the microphone, so I'm going to pass it back to you.
Ken Kadinger, Carnegie Mellon. The goal to do this without subject matter experts, I guess, seems like a sort of fun challenge for machine learning, but practically it seems sort of like, why do that? There are a lot of subject matter experts.
And we're cheap.
And furthermore, engaging them, like teachers, and engaging them in this kind of data analysis would probably improve their pedagogical content knowledge in a relevant way.
Right,
but maybe most importantly, don't we know that better representations lead to better machine learning?
Right.
So getting that input would give us better representations?
Right. I think it's basically what we wanted. Unfortunately, we were not able to, for this deadline, to compare it with how models, like if you actually have an expert and sit down and design a model, how it compares to that. But the idea is not, necessarily to have it like unsupervised, but get some insights from the data that, try to catch the expert blind spots of, oh yeah, this actually might work, and actually use it to refine models. So this is a first step. Yeah, I don't think it makes sense in general to say, let's fire all the experts and let's just let's just replace them by a computer. But like have some sort of way to see if it makes sense what they're doing, or there's an expert blind spot. And also a secondary thing is we really don't know how good our intuitions are in terms of well, we have a collection of mini games in this case. Do all of them make sense? And I didn't get to talk a lot about that, but different games might be better at being able to predict the assessment performance, and a method like this would be able to rank us and give us a sense of get the data to inform us what we're doing right and what there's more room for improvement. But great question, thank you.
Hi, Larry Gallagher from Stanford. I have a couple of contrasting cases. One is a student comes in, is playing these games, you're gathering all this data, you're making a prediction about a post-test, essentially using one form of assessment to validate some function of this other assessment. Another is that the student's coming in and actually learning content playing these games. And I can't distinguish the two cases in your data and how your predictive model distinguishes those cases of somebody who's actually learning over time and somebody who's essentially performing in one environment and then predicting a performance in another.
So I really like this question because it really aligns to what we were really trying to do at the beginning. We were anticipating that, with this brief interaction, this was an experiment that we did. This is not a game that it's popular and we have a lot of data. It was more an experiment. We were anticipating that students were going to learn a little bit. Unfortunately, in this intervention that we had, we don't have any evidence that students learn. The model has these funny or interesting temporal structure. So, it's up to anybody's guess. I think it probably would be able to capture learning, but unfortunately we don't have for now the data to study that question further.
Chase Geigel, UAUC. I was thinking this sounds like something that could be very useful in classrooms where maybe you're trying to incorporate an adaptive learning tool, or even just as some form of dashboard for instructors to be able to, I can have the kids in a computer lab doing this game for a while, and that serves as an unobtrusive way for me to get at least a reasonable feel for which students maybe are struggling with this kind of material and which students maybe are ready to move on to the next area. Have you thought about integrating this with some kind of learn dashboard or active learning, adaptive learning system?
Yeah, I think definitely my colleague Kristen, that's her hope, while designing these games, and also not just saying ranking students, but trying to figure out the learning progression. Well, you're able to do this, but not all. Trying to have a more fine scale assessment, if you may. But yeah, that's definitely, I think, her motivation in designing these sort of games. Thank you.
We still have time for a few more questions, but let me invite the next presenter to get their presentation queued up while we do that. I'll get you next.
Alan Dix, Tallis and University of Birmingham. I've two bits of experience in the past. One was years and years ago analysing Puffin growth data, which had many similar things, and more recently looking at pedagogic data and particularly reading patterns through documents. And in both cases, for puffins growing, little chicks growing, how fast they grew. There were stages, as you described, a bit like you were recovering from the HMM, but how long they stayed in the stage. And similarly with reading a document, if you scan from point A to point B, and you spend 1 second per page, that's quite a different behavior from, say, 5 seconds, which might be a sort of an assessment, or 20, 30, a minute seconds when you're actually reading it. So I was just wondering, just that very simple thing about adding the duration in states back into the HMM, certainly in these cases, you get a huge amount of additional information. And I wonder if that might be the case with your data too.
Yeah, that's a great point. Actually, since we would get that indirectly, since the self-transition probability is my proxy for that, but we didn't investigate that explicitly, which might be interesting. Thank you.
Hi. Does the difficulty of the gameplay increase or decrease with the skill level of the player? And even if that is important in the context of learning?
That might be important, but in this experimental setup, the difficulty was not a function of the student ability. So that makes the analysis a little bit easier in our case, but we didn't have any personalization.
But do you think that will help?
I think it might make analysis a little bit more difficult, right? I think it might be interesting to implement it, but yeah.
Time for one more quick question, if someone has one. Yeah.
The basic idea of your model is that you construct a measure of how well they fit different types of plane, and you use that quality of fitting to predict the scores.
Right.
Now, that's going to work very well in a situation in which how you define the groups, within groups there is very homogeneous behavior. For many educational activities, even for many decision tasks, there are going to be many strategies that are extremely different but lead you to the same level of performance. It sounds intuitively that your method would not be able, as it's specified right now, to cope with that. Have you thought about how to fix that? Fix is not the right word. Extend that, sorry.
Right, yeah, that's a really good point. So I think another way of saying this is that it's not a discriminative classifier in terms like it's not trying to look for the differences in behavior that predicts the output, just like it's sort of like a coincidence. I mean, this method is not obvious that it was going to work, right? You know, like why would high players perform better, you know, perform differently than low performing players? Like, why would they have like a common pattern? So I think like what I'd be interested in looking at is trying to have like sort of like a joint optimization where like the prediction is more like a discriminative way of, yeah.
Thank you very much, Jose.